Let us now introduce the nomenclature in the special case where hydrogen is the cation. When hydrogen cation ionic compounds are placed in aqueous medium, we have what we call an acid. So what I want you to do is, when you see these particular forms of ionic compounds where hydrogen is being used as the cation, I want you to recognize them as acids, given the names that you see on the slide in front of you. Many of them, of course, are very familiar to us. We don't call HCl, hydrogen chloride. We actually do if it's in the gas phase, but if it is dissolved in water, it is known as hydrochloric acid. As a matter of fact, you can buy it commercially as a pool or deck cleaning item known as muriatic acid. H2SO4 would normally be called hydrogen sulfate. What we call it is sulfuric acid. Now, I mentioned previously about the ic and ous suffixes that were used to denote higher and lower oxidation states, and I mentioned that this carries over into the nomenclature of acids, and this is an example of where it does. Sulfuric acid uses sulfur in the sulfate anion in its highest oxidation state. Sulfurous acid with an OUS ending is the sulfite form of a acid containing a sulfur polyatomic anion. So I don't really care so much, just for brevity. You can, as long as you're familiar with sulfuric acid, we'll say that's sufficient. Then below that we have nitric acid. Once again, that is with nitrogen in its higher oxidation state with the ic ending for the polyatomic anion in the acid notation. There's also HNO2 using the nitrite ion. That is known as nitrous acid, NITROUS, to the common folks out there in the chemistry world. Then I show carbonic acid, which I mentioned previously as a very familiar biochemical acid that can be made in aerobically respiring critters who spit out carbon dioxide that mixes with the water in their frameworks and readily forms carbonic acid. So this is a regular material that's used in regulating and buffering all kinds of living system processes. Then the last one I want you to be familiar with would be phosphoric acid, H3PO4. Now again, there would be something called phosphorus acid if you use the phosphite anion, PO3 minus 3. Phosphoric acid is also very important in life systems, in the energetics and Krebs cycle of life systems. Let's move on to the organic compounds known as hydrates. When the polarity of the separated plus and minus charge creates the ionic lattice, as we see here in this representation of sodium chloride, remember, this is a very extensive three-dimensional structure of cations and anions electrostatically connected together. Of course, here I'm only showing it in a two-dimensional form because I have a flat piece of paper. Now what I want you to notice I've done here on the outside perimeter of the ionic lattice is I got a bunch of things that look kind of like Mickey Mouse characters with blue and orangish circles representing water molecules. What happens if you drop a chunk of sodium chloride into water is that the overwhelming number of water molecules present in that solution or that mixture, the so-called solvent, which is present to an extensive excess, inundates the ionic lattice of the sodiums and chlorides and rips their electrostatic attractions apart. This not only dissolves the sodium chloride in the solution, it also does what we call dissociate the ionic lattice, or literally pull it apart into individual plus and minus charges. Now we will have more to say about that in upcoming slides. What I want to focus on here with the idea of the hydrate is, let's suppose we put this chunk of sodium chloride into just the air. But the air isn't simply made up of just nitrogen and oxygen. The air, particularly here in a place like Louisiana, has an abundance of water vapor deposited up among the air molecules as well. So the chunk of sodium chloride laying on a French fry also becomes inundated with water molecules, just not quite the extensive amount that they would encounter in solution. So I have this crystal of sodium chloride, which has, as we can see, a large number of water molecules stuck to the cations and anions. And I've oriented the water molecules specifically to indicate the types of attractions that they would experience to the water molecules. Remember, water consists of H and two H's and an O, the O being the much more electronegative element. And what this means is that it draws the negative charge towards it in the molecule, so that the water molecule's oxygen end is slightly negative. There's a natural permanent polarity to all water molecules. Also, because of the low electronegativity of the hydrogen, the electron density is drawn away from those atoms, leaving them a little bit more of a bare proton nucleus, so that the hydrogen end of a water molecule is slightly positive, and it's permanently slightly positive. So what happens when a huge number of water molecules are floating around in the air and they see this charged ionic lattice of plus and minuses? The water molecules orient, as you may see here, such that the negative ends of water molecules align near the cations, and the positive ends of water molecules align near the anions. If the anions and cations are different sizes than we saw for sodium chloride, the gaps between them can become quite massive. When this occurs, the relatively small water molecules have the ability to work their way completely and homogeneously throughout the lattice. This is what we're trying to represent here on this cartoon we see on this present slide. I have, instead of sodium chloride, I have some calcium sulfide, and what you will notice is the gaps between the ions I'm representing as quite more spacious, which allows the migration of polar water molecules, not only so they have an affinity for the surface of the ionic lattice, but they can work their way entirely throughout the entire structure. The interesting and important thing about it is that this sort of forms a solution with a solid solute, meaning there's a homogeneous distribution of water molecules over the ionic lattice. Around every calcium, there's an equal number of water molecules. Around every sulfide, there's an equal number of water molecules. Now, depending on the size in particular of the anion, there may be more or less space available to allow the water molecules to gather. What this means is, depending on the cation and anion in the structure, in the ionic lattice, there will be different numbers of regularly spaced water molecules incorporated. What we call this arrangement is a hydrate. Now, if you look at a hydrate, it looks like any other normal solid. You can stick a spoon of it into a jar and grab chunks of it out of the jar, and if you hold it up close to your face and inspect it, it won't look, at least from general appearance, any different than any other thing such as sodium chloride. Now, the spaces between sodium chloride are actually too small to incorporate water molecules routinely and regularly within the lattice. But many, many other ionic compounds, especially those with sizable anions, consider things like phosphate or carbonate or nitrate, these bulky anions leave lots of room between them and their neighboring cations, which allows a lot of regularly repeating water molecules in the ionic lattice. So since these are regularly repeating water molecules in the lattice, we must state them in the empirical formula. Now, why this is of greatest importance goes to when we go to use these sorts of things in laboratory. Meaning, when you're in lab, and I'm sure many of you are in laboratory and are familiar with what I'm saying, when we deal with ionic compounds, we don't count out the individual units of them, we weigh them. So I get a jar of a particular ionic substance, take it to the scale, weigh it out, and from the molar mass of that substance, I imply how many individual units of that ionic compound I am using. Well, the problem with hydrates is that when you weigh them out, you will be weighing out, in addition to the weight of the cations and the anions in the anionic compound, you will be weighing out a regular repeating number of water molecules. And this has to be accounted for in the so-called molar mass of this material, and therefore has to be accounted for in the ionic compounds empirical formula. When writing the name of, when writing the empirical formula of a hydrated compound, what you'll note here in this example I'm showing for magnesium sulfate in the hydrated form is after writing the normal empirical formula, showing the cation first, followed by the anion, and of course showing the ratio and proportion of combination that they must make, I have a second molecule representation of the water. And what you'll see here is that what we're stating is that for every one magnesium sulfate cation-anion connection in the ionic lattice, this is surrounded and incorporated by 7 water molecules per unit of MgSO4. So when you think of the ionic lattice, what you should think of is you would have MgSO4, 7 waters. Then MgSO4, 7 waters. And this repeats throughout the entire lattice. Notice one important aspect of the 7 water molecules is you do not incorporate that as a subscript to the water molecules. I write the number of water molecules in the hydrate in front of the waters. So let's be very specific about how I want you to present these, because I will, of course, be asking you to do some of these when we have our next assessment. I first write the empirical formula of the ionic compound as I normally did. I then put a dot to separate how many water molecules are incorporated in that lattice. Then I put an integer, or maybe even a half integer in some cases, which tells how many water molecules are incorporated per unit, and then I write the chemical formula of water. Notice that this is the chemical formula of water that I'm putting in this so-called hydrate. So hydrate is not an anion, it is a neutral water molecule incorporated in the structure. Notice when I'm stating the name, I show the example of that in quotes, I state the name of the ionic compound component exactly the way I would have normally. Magnesium sulfate, stating the cation first, anion second, and remember, no reference to the ratio and proportion of combination. But when now stating the number of waters incorporated in that hydrate, I do state the ratio and proportion of combination. I use the terminology magnesium sulfate heptahydrate, which means for every magnesium and sulfate unit, there are 7 molecular water molecules incorporated. Okay, so what I also would like to point out here is that magnesium sulfate heptahydrate is what is known as Epsom salt. Epsom salts was a very popular analgesic back in the day, not so much maybe anymore, but before the advent of all these pain-relieving medications that are available in modern medicinal chemistry, it had been known for centuries that in some way this particular compound had the ability to ease pain, ease rheumatism and arthritis pains and things like that. So people would dissolve this in warm water and soak their feet in it and do things like that, put their elbow in it, stuff like this. And it was used for hundreds of years in treating ailments of that type. And again, it is known as Epsom salts. A couple of examples of hydrates of the compound calcium sulfate. I see what is known as a hemihydrate, which incorporates a half of a water molecule per calcium sulfate unit. Now, how does it pull that off? Well, you can think of the water as being in between, one water molecule in between each calcium sulfate unit. That would do it. That is known as calcium sulfate hemihydrate, and more familiarly is known as plaster of Paris. This was used, again, for a long time. It still actually does have many commercial uses. We made casts out of it. They used to plaster walls with it before the arrival of sheetrock or drywall, whatever you want to call it. They used this over wooden walls or cement walls or things of that type. If instead of incorporating one water molecule in the regularly repeating lattice of calcium sulfate, but we incorporate 2 water molecules, as we see on the material on the right, I would name that calcium sulfite dihydrate. This commercially is what is known as gypsum. It can be mined out of the ground, and it is routinely mined out of the ground, and then by removal of a little bit of the water, it can be turned into commercial plaster that can be used in a variety of applications to form into molds and things of that sort. This slide shows the first 10 prefixes that I want you to know and use when we are naming hydrate compounds. If the ionic compound incorporates 1 molecule of water per unit of the ionic lattice, we use mono. For 2, di, then tri, tetra, penta, hexa, hepta, octa, nona, and deca. Now there are actually prefixes in the cases that more waters are incorporated. We'll just go with the first 10. I want you to know these. I want you to use them when you have a hydrated compound. If I give you the name of a hydrated compound and expect you to write the empirical formula, you will see me using these prefixes in the written form of the name. Or if I give you an empirical formula that is a hydrate, you will give me these prefixes to indicate how many water molecules, and you will say monohydrate, dihydrate, trihydrate, and so forth, to indicate the number of water molecules in those particular arrangements. So again, please make sure you know these prefixes. I should point out that I think it's obvious these are fairly familiar prefixes that are used in a wide variety of language applications to indicate a certain number of things in a arrangement. Like an octagon, of course, is an 8-sided polygon, and a hexagon is a 6-sided polygon, and so forth. So these terms should be familiar to you anyways. Please, again, I remind you, there will be cases I will give you hydrated compounds and ask you to give me the name. So you should state in front of the word hydrate for them these prefixes. Or if I give you a name including these prefixes and the word hydrate, you should write in the empirical formula a appropriate number of water molecules attached to the empirical formula to represent the right structure. Let's now introduce the concept of an anhydrous compound. An anhydrous compound is an ionic compound that has no water incorporated in its ionic lattice. As a matter of fact, any hydrate can be made anhydrous if you just gently warm it. That drives the water out. I do believe those of you in the 123 class will do an exercise in finding the empirical formula of a hydrate where you will drive water out and you will weigh the compound with water in it, heat it gently, drive the water out, weigh it again to determine how many water molecules are incorporated in the regular repeating lattice. Now, if a compound absorbs water out of the air, we often refer to it being hygroscopic. And this leads to an important trick that has been employed actually for quite some period of time by people when they're trying to keep things from getting damp. We use what we call desiccants to help keep materials dry. You may have seen desiccants if you open up an electronics device that you purchase. In the bottom of the box, there's a little packet, maybe with Japanese, Chinese, or Korean writing on it where these things were manufactured. Then they're put on ships and sent all the way across the Pacific Ocean to get here. And during the course of that transit, these delicate electronics are exposed to a large amount of humid air. And in order to try to protect the delicate electronics from the humidity they encounter, they pack little packets of these ionic compounds that are hygroscopic in with the electronics, and these preferentially absorb water out of the air, which is hopefully done to preserve and prevent damage to the electronics due to the high humidity that they're encountering. As a matter of fact, things like this were also used in the 18th, 17th, 16th, 17th, 18th century in large manors of homes, castles, things of that sort. They could be quite damp and moldy, as you can imagine, in certain environments. So they would stack huge sacks of these desiccant materials in closets to keep the clothes from getting musty. They would put them under the beds and things of that sort to absorb humidity out of the air. Then what they would do is, at the end of the day, they would take the bags, or the next day, take the bags outside, put them in an oven, drive the water out, and reuse them. So they would typically cycle through huge amounts of these things in an attempt at an early, what we would call dehumidifying trick, by using desiccants to keep water out of the air in a particular room. Some examples of the nomenclature of hydrates. Now remember, on the test or upcoming or on my practice pages on inorganic nomenclature, you will see examples of these sorts of things. Remember, I want you to be able to state the name of the hydrate if I give you the empirical formula, or if I give you the empirical formula, you should be able to state the name. In these cases, you can think of me doing it one way or the other. Let's look at the bottom one maybe first, and let's pretend I gave you the name, and the name was calcium chloride trihydrate. What I would first do is use my rules for ratio and combination of a column 2 calcium plus 2 oxidation state cation to a column 17 chlorine minus 1 oxidation state anion. I need 2 takers of 1 to match 1 giver of 2. So the empirical formula of the calcium chloride part would be CaCl2. But since attached to those anion cation names is trihydrate, the tri prefix means 3, hydrate means 3 water molecules. So I put a dot after the empirical formula of the anhydrous form and just write 3 H2Os to represent the 3 water molecules incorporated every time you have a calcium chloride. Now let's go to the top one, and let's pretend I showed you the empirical formula. Cu3PO4.5H2O. And you are asked to write me the name of it. The first thing you would note there is I have a polyatomic anion. It's one of the polyatomic anions we are supposed to recognize and immediately know its structure, formula, and oxidation number. PO4 is phosphate, so that will be what it will be named. PO4 is always a -3 oxidation number, whether the phosphate is combined with sodium, magnesium, copper, I don't care what. So if I will note in the way this compound is structured, I need 3 cations of copper to balance 1 anion of phosphate. Since the phosphates are -3 each, and since there is 1 of them present, I know that the coppers must be donating a total of 3 electrons. Since there are 3 of them present in the empirical formula, that means each of the coppers is giving 1 electron to give the total of 3. So each individual copper is in a +1 oxidation state based on the number of coppers present and the anion it is combining with. Remember, since copper is a transition metal, transition metals can have varying oxidation number depending on condition and material they are combining with. You are obligated to state a Roman numeral that indicates what particular oxidation number the copper happens to be in. So if I were to correctly state the name of this particular empirical formula, you see it to the right. I write copper, Roman numeral 1, phosphate, and then to indicate the number of water molecules incorporated, I write pentahydrate. Now, as a final reminder here, remember, I will be writing, I will be giving you empirical formulas and expecting you to write me the name. Some of them will be hydrated, some of them won't. So make sure you're familiar with what to do in either case. I will be giving you the name and expecting you to write me the empirical formulas. Some of them hydrated, some of them not. So make sure you're familiar with what to do in those cases as well. Let's now turn our attention to molecules. Molecules use a completely different scheme of bonding than ionic compounds. First, we will recognize that molecules are formed when molecules are formed generally when nonmetals combine with nonmetals. So, or as we say at the very bottom there, when metalloids combine with metalloids. So one of the aspects of metal combining with, with nonmetal combining with nonmetal that makes molecules unique is, as we say here at the top, that the combining entities have similar electronegativities. So molecules are going to generally be formed by elements that are combining with themselves or combining with elements that are near themselves in the periodic table. What this means is that now, since the electronegativities are so closely matched, neither element can clearly yank electrons loose from the other. So neither element can force the other element to become an ion. So there's a completely different mechanism by which atoms which are using this type of bonding are capable of connecting to one another. Now notice also we say here that molecules, unlike ionic compounds, molecules exist as individual entities. They do not exist in a lattice. Generally speaking, molecules do not form a rigid structure like we see in sodium chloride. Now that does not mean that it's not possible that you have molecules that form solids. It is possible to have molecular solids. As a matter of fact, you can have molecular gases, molecular liquids, or molecular solids. Almost invariably, the ionic compounds we discussed in the last unit of discussion were all solids. Here, as we get into the details of how these connect to one another, it'll be a little bit easier, I hope, for us to understand why they can take any of the three basic forms of matter. So let's remind ourselves one more time. Molecules are formed by combining atoms that are similar or the same in electronegativity. This means typically that they are nonmetals combining with nonmetals or metalloids. The mechanism by which molecules have atoms which combine together and connect is a different kind of bonding known as covalent bonding. So what is a covalent bond? First of all, we will state unequivocally that a covalent bond can only be formed when the electronegativity of the combining elements is exactly the same. Remember, electronegativity is the desire of an atom to draw electrons to it when it is combining with another atom. So there's essentially a tug of war which is entered into by the atoms that are entering into a combination. What we saw in the ionic compound world was that there were elements of low electronegativity, which were generally larger elements on the left side of the periodic table, which preferred to become cations. These were the metals in an ionic compound. They combined with so-called nonmetals in the upper right-hand corner of the periodic table, which were relatively smaller atoms, which by their size allowed incoming electrons to get closer to their nuclei and therefore had a greater desire to gain electrons. So when these two got into proximity, there was a transfer of electron from the metal to the nonmetal, making a cation of positive charge, an anion of negative charge, and they stick together. Now here, the atoms are of exactly the same electronegativity, so neither has the ability to pull the electron loose from the other, so they could fight an eternal tug of war over the electrons. But what happens is, rather than do that, they decide, well, why don't we share the electrons between us? We will have equal control of these electrons, and if I need some, you will put them into a share, and if I need some, You, or vice versa. If you need some, I will put them in. If I need some, you will put them in. We will at all times think that we control these electrons, even though they are in this, so if we want to think of it as a co-op of electrons between the elements. So the idea behind covalent bonding is that electrons are shared rather than transferred. Let's begin with the simplest of all possible covalent bonds. The covalent bond which connects a hydrogen atom to a hydrogen atom in a diatomic hydrogen molecule. We see here representations of the Lewis dot structures of each individual hydrogen atom. Remember, each hydrogen atom is in column 1 and has one valence electron. Now, the electronegativity of HA is exactly the same as the electronegativity of HB, so that neither could win a tug of war over these electrons. So what they end up doing is they each just contribute an electron into a sharing zone. So what I show in the middle of the slide is a circle representing the sphere of influence of hydrogen A and a circle representing the sphere of influence of hydrogen B, and there is an overlapping region of influence between those circles, which constitutes the covalent bond between these two hydrogen atoms. Notice that each hydrogen places its valence electron into that sharing region, so that at any given time the hydrogen on the left thinks those two electrons belong to it. At any given time, the hydrogen on the right thinks that those two electrons belong to it, and they are completely shared by the two hydrogens. So the bonding region is the region between the two nuclei where there is enhanced electron density due to the sharing of electrons by the two atoms. Now, this has the effect of allowing the nuclei to get into closer proximity to one another. Remember, the nuclei are positively charged. And so now what we're saying is that the positive charge of H on the left is shielded from the repulsive positive charge of the H on the right due to the presence of the shared bonding electrons between those nuclei. So this allows the H2 atoms to get into closer proximity to one another than would be expected in a normal electrostatic situation. So this is how we will draw the Lewis dot structure. Now, do you have to put the spheres of influence and show the circle of overlap where the electrons are shared? I really don't care that you do that. I'm doing it for demonstrative purposes, showing a bonding region localized between the two hydrogen atoms. You do not have to put these circles. You can just connect HA to HB by putting a dot from A in the middle and a dot from B in the middle. Now, one more thing I would like to mention here is that electron pairs constitute a bond. And in particular, the electrons are paired because one of them is in the spin up or m sub s plus 1/2 notation. One of them is in the spin down or m sub s minus 1/2 notation. Remember, this allows electrons on a given atom to climb into the same orbital at the same time without interfering or repelling one another. Likewise, in a chemical bond where electrons are shared between atoms, an electron in a spin up and a spin down configuration allows those two to get into this close proximity to one another. They don't even know each other is there in actuality, so that they can create this buffer or shielding of the positive nuclear centers from one another and allow the nuclei to get really close together and form this covalent bond. Now let's turn to the Lewis dot structure of F2. F2 is a column 17 element. As you see here, it has a 7-dot Lewis dot structure. And of course, each fluorine needs one more electron to complete its octet. Now, if Fa attempts to get this electron from Fb, what it will soon become apparent is that the electronegativity of each being exactly the same, it precludes either from winning the electron pull from the other. So each fluorine takes one of its valence electrons, places it into a sharing zone between the Fs. These electrons pair, spin up, and spin down. And so in the overlapping region of influence of each of the two electrons, or of each of the two atoms, I place those electrons. If I count the valence electrons around the F on the left, I would count 2, 4, 6, 8. If I count the valence electrons of the F on the right, I would count 2, 4, 6, 8. So in this way, each of the fluorines has the sense that it has completed its octet without the benefit of an electron transferred from another, particularly a metal, which became a cation during the process. So what you should think of here in a case like this is that there's a lack of polarity to the bonding characteristic between the way the electrons are shared in this covalent situation. Electron density is evenly distributed between the fluorines, so neither of them is net positively charged or neither of them is net negatively charged, unlike what we saw in the ionic compound. Now again, what I want to point out also is that this truly constitutes a chemical bond. In the ionic idea we discussed previously, we did call those ionic bonds, but really technically, as I said to you many times, they are really ionic attractions. Here truly, the sharing of electron density by atoms constitutes a true electron bond between the atoms. Now, when I share a single pair of electrons, one spin up, one spin down, I'm going to know that as a single bond. So one shared pair of electrons from here on out will be called a single bond between the fluorines. It holds them together, unlike the electrostatic attraction, which was possible in the ionic arrangement between metal and nonmetal. Another thing I would like to point out is that the covalent bond, believe it or not, is a much stronger attraction between the atoms entering into this connection. Now, we have evidence of this when we place covalent molecules in water or ionic molecules in water. The polarity of water, it turns out, is sufficiently to rip apart ionic bonds between sodiums and chlorines, making free individual sodium cations and chloride anions floating in the solution. However, for covalent attraction, say between these two Fs, if I dump a bunch of Fs into a solvent of water, the polarity of the water molecules is not sufficiently strong enough to pull the F2 apart, making an F plus cation and an F minus anion. Again, this is evidence of the strength of a covalent bond compared to the strength of an ionic bond, and the fact that a covalent bond is stronger than an ionic bond. Here we demonstrate the interesting case of the covalent bond formed by connecting two oxygens together. Again, let's refer to this based on the Lewis dot structures rather than on oxidation numbers, and we will do this basically for all of our covalent molecules. I look at the Lewis dot structure of two oxygens and note they are each in column 16. Being in column 16, they have 6-dot Lewis dot structures, so each oxygen requires 2 more electrons in completing its octet. Oxygen on the left will get those 2 electrons from the oxygen on the right. The oxygen on the right will get the 2 electrons it desires from the oxygen on the left. Now remember, because their electronegativities are exactly the same, neither can pull these electrons loose from each other. And of course, again, sharing 1 electron between the oxygens will not satisfy the needs of the other. So each oxygen will put 2 electrons into the sharing zone, as you see in the middle cartoon. And we have a total of 4 electrons placed into this sharing region. Now once again, they are in spin up and spin down conformations, so we have 2 shared pairs of electrons in the bonding region. Now again, notice in the circle of influence of the electrons on the left, I can count 2, 4, 6, 8 electrons total, including the non-bonding or unshared electrons on O on the left, plus the bonding or shared electrons of the O on the left. I can count 2, 4, 6, 8 electrons seemingly around the oxygen in the right sphere of influence, indicating those are the 8 valence electrons it desires, and it has completed its octet for the oxygen on the right. So unlike fluorine, where there was a necessitated to share 2 electrons total between the 2 Fs, here we have 4 electrons shared between the 2 Os. And what we again do is we think of these in terms of pairs. So we have 2 shared pairs, which we call a double bond between the oxygens in this region. Later we'll talk about and compare and contrast the properties of double bonds compared to the properties of single bonds. Let's continue this by looking at the Lewis dot structure of N2. Now N each is in the 15th column of the periodic table. That's a column where the elements have 5 valence electrons, represented by the 5 dots you see around the 2 individual atoms. Again, each nitrogen seeks to complete its octet, but neither has the electronegativity to pull electrons loose from a cousin of itself. So rather than fight a tug of war, they decide to share. And since the N on the left needs 3 more electrons, it must get them from the N on the right. Since the N on the right needs 3 more electrons, it must get them from the N on the left. So each nitrogen atom will contribute 3 of its valence electrons to the sharing zone. That leaves 2 non-bonding, or as we will call them, lone pair electrons outside the sharing zone. And again, we should think of those shared pairs of electrons in spin-up, spin-down conformations. So we have 3 shared pairs in this particular arrangement, which we will call the triple bond of electrons between the 2 nitrogens. On this slide, I show you the elements which occur in nature which are naturally found as diatomics. The list of them is short, and as a matter of fact, I expect that you know these 2, 4, 6, 7 elements, and the fact that they, when you find them in their atomic form, you do not find them as monatomics, you always find them as diatomics. So we have H2, N2, O2, F2, Cl2, Br2, and I2. Notice the name of them is not given any special consideration, any change to the typical atomic name. And again, if you work with elements of this type, this is how they always exist, or this is what we call their standard state in nature. When we find oxygen in nature, it is in the form of O2. When we find bromine in nature, it is in the form of Br2. Now again, I want to remind you that you can expect that I will ask you somewhere along the line so that you can indicate to me that you are in some way familiar with the limited number of elements that exist as diatomics in their so-called standard states. We already talked about the Lewis dot structure of fluorine. Let's talk about the Lewis dot structure of its column of cousin elements, which are collectively known as the halogens. This would include chlorine, bromine, and iodine. As we talked about on the previous slide, all of these are diatomics in their natural form, meaning they exist in nature as molecules, covalently bonded sets of two atoms. And since each of these has 7 valence electrons, since each of these is short by 1 electron from completing its octet, each of these will form Lewis dot structures in the diatomic form of the type you see below, where a single pair of electrons is shared between each of the two atoms in combination. Now notice in this instance I didn't draw the spheres around them, and I don't expect that you, or you could if you want, I don't really care, but you don't need to draw the spheres of influence around each. Just recall that electrons placed in the central region are commonly shared electrons, which allow the positively charged nuclei to get into closer proximity to one another. So we have, for each of these, 2 so-called bonding electrons, and each of these atoms has 6 non-bonding electrons. Let's look at the structure of column 16 diatomics. Remember, this is the column headed by oxygen and includes sulfur, selenium, and tellurium. These are all 6-dot Lewis dot structures. Each atom in this column requires 2 more electrons to complete its octet. And if those electrons are being procured from one of its cousin elements, then each of those elements will have to give 2 electrons to the other. Since they're each, again, short 2 electrons, the only place they're getting those electrons are from its bonded partner. So each atom contributes 2 electrons to the sharing region. That gives each of those elements, as we see there, a complete octet, where there are 4 total bonding electrons between them and 4 total non-bonding electrons on each. So each has a so-called completed octet of these electron arrangements around them. So again, what we might say here is, since the column 16 elements are isovalent, meaning having the same number of valence electrons, then each of the column 16 elements could form the same type of diatomic structures. Now notice, one thing I would like to point out is that in nature, sulfur does not exist as S2, selenium does not exist as Se2, tellurium does not exist as Te2. Only oxygen exists as O2. The other ones actually connect to each other in different ways. They're actually they're non-metallic, but they are solid under typical ambient conditions, unlike oxygen, which of course O2 is a gas which we breathe in routinely. Now I'm not so concerned about that fact. We still should be able to draw Lewis dot structures for S2, Se2, or Te2, showing the correct way to connect them so that each element has its complete octet. But just keep in mind the fact that in actuality, in nature, only oxygen exists in the diatomic form. Continuing with this idea, we can now discuss the diatomics that are possible to form from column 15 elements. Remember column 15 element headed by nitrogen. All elements in that column have 5 Lewis dots. To complete their octets, all elements in that column require 3 more electrons. If they're going to attempt to get them from an element of equal electronegativity, they will have to share electrons with that other element. So each would have to contribute 3 electrons to the sharing zone. And we see that there's a triple bond, 3 shared pairs of electrons between 2 nitrogens, 2 phosphoruses, 2 arsenics, or 2 antimonies in the attempt to make covalent bonds between them. Notice each element of this column 15 group would have 1 remaining lone pair of electron, and that each looks as if it has 8 total valence electrons, counting the shared and non-bonding electrons that each claims to control. Now, another thing to keep in mind is that each N had 5 valence electrons, so there are 2 N's combining. That's a total of 10 valence electrons, and you will note by the way the dots are arranged around N2, there's a total of 2, 4, 6, 8, 10 valence electrons represented. We don't add extra electrons into the mix. We don't leave any out. Phosphorus, likewise, each phosphorus contributes 5 valence electrons. It's a total of 10 valence electrons to share between them. And the way that they can be arranged so that each thinks it has a complete octet is that there are 6 total in the sharing zone and 1 non-bonding pair on each phosphorus. Let's now turn our attention to the third type of bonding, which we will describe. And this third type of bonding, which is known as the polar covalent bond, will be the last type of bonding which we will add to our way in which we can connect atoms together. And as we say here on this particular slide, this polar covalent bond is kind of an intermediate. It's actually a combination of the other 2 types of bonding, which are the covalent type and the ionic type. Reminding ourselves, an ionic bond is formed between metal and non-metal. It's formed between elements with large difference in electronegativity. And a covalent bond is a metal-metal or metalloid-metalloid bond, where the atom is combining with another atom of exactly, and I will say exactly, the same electronegativity. So a polar covalent bond is an intermediate of the covalent or the ionic bond, as the name implies. Polar is the ionic part of the name, covalent is the sharing part of the name. The polar covalent bond is formed by elements that have electronegativities which are not exactly the same, however, they are not dramatically different. So polar covalent bonds are formed by elements that have what we will call similar electronegativity. Now, what do we mean by similar? Well, typically these are going to be metal with, these will be non-metal with non-metal, or non-metal with metalloid, but they are just not non-metal with non-metal of exactly the same type. These are not CC bonds, these are not OO bonds, these are not O or NN bonds. Polar covalent bonds can be elements of similar electronegativity that are non-metal with non-metal, such as N with O, such as S with O, such as C with N. So what we will say is that the polar covalent bond is formed between elements that are near each other in the periodic table. They are not elements combining with themselves. They are not elements combining that are far apart in the periodic table. They are elements that are combining with other elements that are near each other, implying they have similar electronegativities. So as a review, Ionic bonds are formed by elements with large difference in electronegativity, meaning elements far apart in the periodic table, typically metal with nonmetal. Covalent bonds are formed by elements with the same electronegativity, literally meaning elements combining with themselves, most commonly nonmetal with nonmetal or metalloid with metalloid. And polar covalent bonds are formed by elements with similar electronegativity, meaning they are elements that are near each other in the periodic table. Typically, again, nonmetal with nonmetal, it's just nonmetal not bonded to itself. What I'm going to expect that you are able to do is that if I give you a molecule that is a combination of atoms, or a compound for that matter, that is a combination of atoms, you should immediately be able to identify the type of bonding that collection of atoms is using. How you do this is by recognizing the relative location of the atoms in combination in the periodic table. So we have these 10 different species that you see on the slide in front of you, and the question would be, which of the 3 types of bonding does each of the following use? Now, again, remember, they're only going to use one of these types of bonding, and again, it's going to be based on the relative electronegativity of the combining elements. Again, recapping, if elements are combining with exactly the same electronegativity, they are using covalent bonding. If elements are combining with similar electronegativity, they are using polar covalent bonding. If elements are combining with dramatically different electronegativity, they are using ionic bonding. The first example is Cl2, which is an atom combining with itself, and the electronegativity of the 2 Cls is exactly the same, so it is using covalent bonding. Next we have PCl5, and if you have a periodic table available, you will note these are 2 elements near each other in the periodic table. They therefore have similar electronegativities, so they must use polar covalent bonding. Then we have SO3, which is a polar covalent, again, combination, because the S combined with the O are elements near each other in the periodic table. Now, before we move on from that one, I would love to point out here that many of you might be thinking that this is ionic because it is sulfite. Well, what I will argue to you is, as we will see in upcoming slides, this is not sulfite. Sulfite is SO3, yes, but sulfite is SO3 minus 2. This is a neutral combination of S with 3 O's. And in this neutral form, the S and O of similar electronegativity are polar covalently combining. Then I have the situation of K combining with F, potassium fluoride. Those are elements of a metal with nonmetal. That is a ionic combination of materials. H2, element with itself, covalent. Next row, we see Li2O, element far from the left, combining with element far from the right, ionic arrangement. Then we have NF3, which are 2 nonmetals combining together of slight difference in electronegativity, making it polar covalent. Next, we have magnesium sulfate. And what I want to point out to you is that when you think of the S combining with the O to make sulfate, you're thinking that that must be polar covalent to put those 2 together. But the way in which you build sulfate is that you need 2 extra electrons thrown in with the 4 oxygens and 1 sulfur to construct the sulfate anion. And this does so by stealing 2 electrons from a metal, in this particular case, the metal being magnesium. So even though, again, SO4 internally is polar covalently connecting the S to the O, globally, to put the sulfate together with the magnesium, I will prefer that you refer to that as being ionic. Next we have Br2, which of course is atoms combining with itself, being covalent. Then finally, we have the representation of calcium nitrate. Once again, nitrate internally is polar covalently connecting N to O, but to build nitrate, you need an extra electron added to the mix. That extra electron is received from the calciums one at a time for two individual nitrates, making it overall an ionic compound when you connect a nitrate to a calcium. Let's now describe the nomenclature which we will employ for molecules. Now, because of the nature by which molecules can combine with one another, what we're going to find is that there are multiple ratio and proportion of combination between these materials that are either covalent or polar covalently bonded. As a matter of fact, particularly in the polar covalent case, most familiarly, we're all aware that carbon can combine with oxygen as CO. We are also well aware that carbon can combine with oxygen as CO2. So to differentiate those two, we can't really use Roman numerals for their to describe their oxidation numbers, because technically they're not transferring electrons between each other as much as they are sharing electrons. So in these situations where you're forming molecules as compared to compounds, in order to tip people off as to the varying ratio and proportion of combination, we again turn to prefixes to indicate the number of combining atoms in the collection. The prefixes we use are exactly the same as we used in hydrates. Again, here I'm only going to list the first 10, but you will note they are exactly the same as those that are used in hydrates, so that at least in one regard makes them easier. Now, what we are going to then state is that anytime we do a polar covalent molecule, where elements have similar electronegativity, you must employ these prefixes in stating the name of those materials. Again, you must use prefixes for molecules, which are entities that exist as individuals rather than compounds, which are concatenated over and over and over again. So anytime I have non-metal on non-metal polar covalent bonding, I'm going to want you to use prefixes in the description of the names of those particular materials. Some examples of the nomenclature of molecules. Let's pretend I gave you the name and you were charged with giving me the empirical formula. First, I offer the example of silicon tetrachloride. Now, that implies that I have an Si connected to 4 chlorines. Now, notice one interesting point with regard to this is I still use the IDE ending for the second named material, just like I did in the ionic nomenclature. So that is a holdover from the ionic, or it's the same convention in the ionic and the polar covalent nomenclature. So carbon monoxide is a carbon combined with a single oxygen. Now what I want you to notice in that regard is we don't use a syllable of mono for the first element listed, only a syllable of mono for the second one listed. Above, for instance, that is not monosilicon tetrachloride. We call it silicon tetrachloride. And the second one is carbon with 1 oxygen, so I call it carbon monoxide. Likewise, the third one is sulfur with 3 oxygens. I don't call it monosulfur trioxide. I call it sulfur trioxide. Now the next example is a 2-atom case for the first element, and in that instance I do use the dinitrogen prefix to go with the pentasulfide. Then finally for the P4O10, that would be tetraphosphorus decoxide. Now you'll notice some of you might have spelled that decaoxide, but typically we don't put the 2 vowels together in a case like that. So that would be how we would give the name of the P4O10 combination that forms a polar covalent molecule. Some more examples of the nomenclature of molecules. Let's suppose here I'm giving you the empirical formula, you give me the name, which of course when we have our little assessment upcoming, I will expect you to go one way or the other. If I gave you the symbol CO2, that would be carbon dioxide, no mono on the carbon, notice. I2O5 is diiodine pentoxide, N3S7, trinitrogen heptasulfide, P2S6 would be diphosphorus hexasulfide. What I would now like to point out is that there are special case molecules which many, as you can see here, contain hydrogen that do not adhere to the syllabic numeric prefix naming convention. This is mainly because many of them have been around for quite some lengthy period of time before there was a systematic naming nomenclature system that was adhered to for molecules in general. So not surprisingly, these are some of the more familiar materials that have been around in nature and have been used by humans for quite some lengthy period of time, again, before these things were conventionalized. For instance, H2O is never called dihydrogen monoxide. It is always called water, of course, or agua in Spanish. NH3 is never known as nitrogen trihydride. It is ammonia. And CH4 is never known as carbon tetrahydride. It is always known as methane. Now, the last case that you will see there is an example of what we call an organic molecule, one containing carbons and hydrogens, and sometimes a smattering of other things, but essentially the main gist of organic molecules is carbon combined with hydrogen. Below the top 3, you will see other polar covalent molecules that involve connections of carbon and hydrogen, which we will look a little more closely at how to construct in our next set of slides. But for now, I want you to note that we have things such as ethane, propane, butane. We could continue this system to the nomenclature of a wide variety of so-called hydrocarbon molecules. When you take your organic chemistry, you will stress how to the various taxonomies of these molecules. That will be an emphasis in that particular class. I'm sure we have heard of something such as octane, which is an 8-carbon chain of carbons connected with hydrogen. There are other things such as hexane, heptane, pentane, and on it goes to show how we can combine connections of chains of carbon atoms together sequentially in organic molecules. One more thing I do want to mention is that I said that these polar covalent molecules are essentially nonmetals combining with each other, and you might be surprised to note hydrogen can be, in some instances, ionic when it forms acids, but in some instances it can also be molecular. This is an unfortunate artifact of the behavior of hydrogen. hydrogen is really much more like a nonmetal than it is like a metal for sure, for certain. And when hydrogen combines with oxygen, with fluorine, with carbon, with nitrogen, we will consider it as a nonmetal. When hydrogen combines with other materials such as nitrate, sulfate, carbonate, we're going to consider it as behaving ionic. So unfortunately, this is something you just have to familiarize yourself with as you get more comfortable with chemistry. But for now, I want to just point out again, hydrogen is kind of bizarre. It can play non-metal games and form molecules. When combined with certain other nonmetals, it can also form ionic compounds in the form of what we call acids when it combines particularly with polyatomic anions.